All right, guys. Can you? All right. Can you guys hear me? All right. Cool. So, hi, I'm Sagar. Krista and Vlad are at faculty retreat today. So I'm going to be covering lecture for today. So we're going to be talking a little bit more about I/O. So we're going to jump into DMA, then cover a little bit about disks and networking towards the end. A quick 61C in the news. So this is admittedly not that new, but in 2014 in ISCA, which is the International Symposium on Computer Architecture, Microsoft announced this thing called Catapult. So the idea is that Microsoft takes FPGAs, which are essentially programmable hardware, and they stick them in data centers, and they put custom hardware next to data center machines to accelerate certain applications. So in this case, they took Bing, which is Microsoft Search, and they were able to get 95% more throughput for only 10% more power. And ultimately, they could relieve their CPUs of doing some of this lifting and dedicate them to do other work. So essentially, the way FPGAs work, they lie somewhere between having application-specific circuits, like a custom circuit, and a general-purpose CPU. So general-purpose CPUs are cheap because they're built kind of mass market, but they're not necessarily the best tool for every application. Sometimes we want custom chips, but they can cost anywhere from hundreds of thousands of dollars to millions of dollars to make. So we have this thing in between. An FPGA is essentially a bunch of tables where we can program essentially the truth table for a series of gates using a stream of bits, and we can build custom hardware that way. So there are FPGAs in data centers now, so if you need a motivation to take CS150, there is actually still relevance even in industry, even if you're not doing pure hardware design. And a quick plug for doing research at Berkeley. So this is a recent project that's very similar to what Microsoft did. So there's this data center application called a key value store. So if you've worked with dictionaries in Python, the idea is that you index on a key and ultimately you get some value out of it. So there are distributed key value stores that run in these data centers that serve lots of the data for many of the applications you use on the internet. In this project, we found that in data center applications, about 86% of request latency is actually just time spent in the CPU executing stuff. So you might think that maybe all of that time is wasted on the network, but really Amdahl's law tells us that we should be tackling the problem by trying to take the CPU out of the loop. So one thing that we did was we built a key value store in hardware, sort of. So we put a cache directly next to the network interface card, and it interfaced through DMA, which is something we'll talk about today. And we got like a 10x reduction in latency. So you can go talk to professors at Berkeley, and they'll be happy to let you do cool stuff like this. They'll give you nice toys like this board that we used, and you can build lots of cool stuff. So, okay, so jumping into our actual material for the day. So a quick review of last time. We talked about programmed I/O. So the basic idea of programmed I/O was that the CPU is going to execute a bunch of load words and store words to actually interact with external devices. So the notion of memory mapped I/O is also very similar, right? So we have certain addresses that map to devices rather than actual chunks of physical memory. And the idea with programmed I/O is that your CPU executes these instructions to interact with devices, but the CPU also uses these loads and stores to interact with the data that the devices provide. So this means that when you're dealing with devices, the CPU really spends time doing three things, when really it's only good at one of these things. So the first is actually just getting data from the device into main memory. So the CPU is actively involved in doing this. So the CPU is going to issue a bunch of loads to whatever address represents the device to get data. Then it's going to apply some operation on that data and store it back into main memory. And that's how the CPU kind of captures data from devices. And we'll learn about a replacement for this that works much better in practice. We also learned about polling and interrupts. So polling and interrupts are two ways of interacting with devices in terms of kind of figuring out when we want to start our interaction. So there are two options here. There's polling, which means that we as the CPU keep asking the device whether or not it wants data or whether or not it has data for us. So this works really well for devices like mice, where the mouse is really giving you like constant data, right? It always knows where its position is. And if we use interrupts in that case, we would flood the CPU with data. Really, all the CPU needs to do is get enough data from the mouse to update the cursor position so that the human looking at the screen kind of thinks that it's a smooth motion, right? So we use polling in that sense, so the CPU keeps asking the mouse for its current position. On the other hand, with interrupts, the device itself will keep signaling the CPU and tell the CPU that, hey, I have device ready, or hey, I want some data from you. And now it's the CPU's job to just kind of drop whatever it's doing and go handle that request. And last time we learned about how interrupts fit into our 5-stage pipeline. So I mentioned when we want to work with real devices, programmed I/O isn't necessarily the right approach. So we're going to use this thing called DMA, and what DMA is going to do is it's going to get rid of the requirement that we have to use load words and store words to fetch data from our devices. So we're still going to use load words and store words to configure our devices with memory mapped I/O, but now the CPU is only really dedicated to doing one thing. Now there's going to be some other device that gets data from the device and puts it into main memory. And then the CPU's only real job is to actually do the computation. And so we'll talk a little bit more about that in the next couple slides. So here's our agenda for today. So we're going to start talking about DMA. Then we're going to move on to talking about disks. So it'll kind of motivate why our virtual memory system is designed the way it is, because in the end, virtual memory is really designed just to bridge main memory and disks. And then we'll step a little bit into some more complicated I/O, so networking, so I/O between computers. Okay, so we talked about this a little bit, but just to formalize it, what's wrong with programmed I/O? Well, when we're dealing with programmed I/O, the CPU is kind of the device that has sole control over main memory. So even though there are really other devices that would like to work with main memory, it's the CPU's job to arbitrate what has access to memory and what doesn't, right? So this means that the CPU is kind of micromanaging all of the devices. So whenever something wants to write into memory, it's really the CPU that's taking data from that device and storing it into memory. So this means that the CPU has to be the one executing all of the transfers, when really it could be doing better work. It could be doing heavy computation that doesn't require memory accesses and things like that. So we want the CPU to be doing what it's actually good at, which is computation. Another reason is that device speeds don't align well with CPU speeds. So usually devices are much slower or much faster than a CPU is able to handle, which means the CPU kind of wastes a lot of time interacting directly with those devices. And then our last reason is a more important reason kind of as time goes on, and that is energy cost. So when we use a kind of beefy general purpose device like a CPU to do computation that simpler hardware could do, we end up wasting a lot of power and energy. And as we know, Moore's law is kind of starting to get stuck, and all kinds of scaling are starting to get stuck. So we don't have the same power budgets we used to have when we were building chips and just making the transistors smaller and smaller. Okay, so what is DMA? So DMA stands for Direct Memory Access. The idea is that other devices, besides just the CPU, are now going to be able to directly interact and read and write from memory. So in order to allow this, we're going to introduce a new piece of hardware called the DMA engine. And it's the DMA engine's job to take instructions from the CPU. Now, I don't mean machine instructions. I mean like information about what to do. So it's going to take instructions from the CPU, and the DMA engine will then use that information to control how the different devices interact with main memory. So some of this information is stored in registers that the CPU has access to. So the CPU is still going to do memory mapped I/O to actually interact with the DMA engine. So it's going to do things like tell the DMA engine how much memory or where to place data, so which memory address that data should come in and out from, the number of bytes of data the CPU is either willing to accept or willing to send out, then which device we want to send to, so the I/O port number, and the direction of the transfer, whether we're sending data in or out. And then lastly, the unit of transfer, so that could be bytes, it could be words, or maybe something larger. And then the amount to transfer per burst. So we'll see some issues later on with how the CPU shares access to memory with the DMA engine itself. And so we have to decide how much data we want to allow the DMA engine to write into memory at a single time. All right, so a very simplified diagram of the difference between programmed I/O and DMA. So we have a bunch of devices, right, hooked up directly to the CPU, and the CPU is kind of in the way between their accesses, what they want to do, and memory, right, what they want to access in memory. So on the other hand, with DMA, we're essentially providing a direct connection between devices and memory. So a slightly more, architecturally specific diagram of a system with DMA. So we have this model of a shared bus. So there's one bus that everything communicates off of. So by bus, I just mean a bunch of wires. And so everything is connected to this bus. So the DMA controller is connected to this bus, the CPU is connected to this bus, and so they need to work out some way to decide who gets to access memory, right? So in this case, there's only one way to access memory at a time. And so you need some method of arbitration. And so we'll talk about some of the issues there in a couple of slides once we talk about how the system works. But now we notice that devices plug into the DMA controller, and they might have one or two wires going to the CPU just to interact at a very high level, so a very kind of managerial level rather than a data transfer level. Okay, so now we want to worry about how the actual transfer happens. So obviously there are two things that could happen. We might want to send data and we might want to receive data. So if we're doing DMA and we're looking for incoming data, what's going to happen is we're going to receive an interrupt from whatever device wants to give us data. And the CPU is then going to take that interrupt and start the transfer. So this means that the CPU has to tell the DMA engine where to place data, how much it's willing to accept, and how to go about actually doing that transfer. So once those instructions are passed to the DMA engine, the CPU is kind of free to go do whatever it wants, right? So potentially there are multiple programs running on the CPU, so the CPU can switch out to a different application that's not waiting on this I/O. So the device and the DMA engine will handle the transfer in the background while the CPU does other stuff. And then once the device and DMA engine are done doing the copy, they'll interrupt the CPU to say, hey, here's the data you wanted, and now you can go process on it. So that's how we're going to handle incoming data. And we'll take a very similar approach to handling outgoing data. So here, we're going to say the CPU is the one that wants to initiate the transfer, so it's sending something to someone else. So it's going to initiate the transfer. It's going to confirm that the external device is actually ready to accept data. So it'll do that through normal memory mapped I/O without DMA. Then the CPU is going to start the transfer. So to do this, it's going to tell the DMA engine where the data is located. So at some point in the program, it had to copy data into a place that's accessible to the DMA engine. And then the DMA engine will go and handle the transfer in the background. And once again, the CPU is free to go do whatever it wants. And once the transfer is done, the device and DMA engine will interrupt the CPU again to say that the transfer has completed. Okay, so as usual, when we start making architectural tweaks, we're going to introduce some new issues that we have to worry about. So the first of these is to decide where in the memory hierarchy we're going to plug things in. So far we are dealing with the nice pyramid-shaped memory hierarchy where there was one CPU at the top, and maybe we had multiple CPUs too, and we had some cache coherence protocol, right? So this DMA engine is going to look very similar to another core in our system. So we need to decide where to plug it in, and that's going to determine how hard it is to get cache coherency, and at the same time how it's going to determine how well our caches actually work for the computation that the CPU is trying to do. Okay, so there are two extremes here. We can plug the DMA engine in between the L1 and the CPU, so we can add a port to the L1, the top of the L1 where the CPU also plugs in. And so this is going to give us free coherency, right? So there's no memory structure now that's dedicated either to the DMA engine or to the L1. All of the caches, all of the memory structures, they're all shared. So we get free coherency without modifying any protocols or anything like that. The problem here is that whenever we accept or want to send out something using the DMA engine, we're going to end up trashing the CPU's working set, right? So presumably the point of having the DMA engine, right, is to let the CPU do other work, which means the CPU is going to need to access some data. So if we do this, right, and we send all of our DMA memory requests through the cache is now shared between the data that the DMA engine is writing and the data that the CPU is trying to use, right? So what we mean by trashing the working set is the DMA engine is going to be doing lots of writes into memory, and it's going to end up kicking out things that the CPU is trying to use. What's wrong with that? Any ideas? So what was the point of having DMA? Is that we could do processing and we could have data transfer happening at the same time. Well, if we've trashed the CPU's working set, now the CPU has to go interact with memory, and the DMA engine is trying to interact with memory, and so one of them is going to get stuck. So maybe this isn't the greatest approach. We can also try hooking this up between the last level cache, so our L4, whatever is right before main memory, and main memory. And the pro here is that we don't mess up our caches for the application that's running. So whatever data the CPU is using will stay in the upper level caches, and the upper level caches, unless we do something special, will have no knowledge of this new data coming into main memory. But this lack of knowledge is going to cause a problem in terms of coherency, right? So now if the CPU, so admittedly this is bad design, but if the CPU is working in the same area of memory as the DMA engine is working, then we're going to get coherency problems, right? The upper level caches are going to have no idea that whatever is backing them is going to be changed by the DMA engine doing lots of writes. And so in this case, we need to modify our hardware to explicitly manage coherency, and this adds some complications. Okay, then we have this other problem of actually arbitrating between the CPU and the DMA engine when we're accessing memory. So let's assume we went with the last approach, right? So the last approach on this slide that doesn't end up trashing the caches. Now we need to figure out how to arbitrate between two things that want to access a single memory. And so this goes back to our kind of unit of transfer that we were talking about earlier when we talked about transferring in bursts. So there are three options here to decide between who gets priority access to memory when we're doing these transfers. So first we have burst mode. So burst mode says the DMA engine is starting to transfer a block. This means that the CPU can't access memory anymore until the transfer is completely done. Now, this works great for devices that want to give you a ton of data at once, and they don't have the capacity to store that data that they're generating within themselves. So in that case, we have to have burst mode, and the CPU has to wait. The other option, or another option, is cycle stealing mode. So in cycle stealing mode, what we do when we're doing the transfer is we ask for permission to use the system bus, right? So we had that one single bus that connected everything. We ask for permission to use the bus, then we transfer a byte, and then we immediately release control of the bus so that the CPU can go fetch an instruction or whatever it needs to do. And then immediately we ask for control of the bus again, transfer another byte, and we keep doing that, right? And so we can adjust the size that we transfer at once, but ultimately we're really, in this case, interleaving processor memory accesses and DMA engine memory accesses. Okay, and then our last option is something called transparent mode. So this works great when we want the CPU to be constantly working and we don't want anything to get in the way of the CPU. So what happens is, in transparent mode, the DMA engine will constantly be looking on the bus to see if the CPU is doing any work. If the CPU is doing work on the bus, for example, accessing memory, the DMA engine is going to back off and not do any transfers. So it's only going to do any transferring at all when the CPU is not accessing memory. Okay, so a quick administrivia slide. So HCAN core surveys are on Tuesday, so please come so you can tell us how we did. Midterm 2 scores are up, as was on the slide on Tuesday. The regrade request deadline is this Sunday. We fixed this small bug with potential multiple interpretations of one of the questions, so you should see regrades for those kind of happening automatically over the next day or so. The Project 4-1 due date is extended to Wednesday. And Project 4-2 is still due Sunday, May 3rd. So all you're doing in Project 4-2 is running your code on EC2. So we figured that would be pretty boring for you while you're waiting for that EC2 job to complete. So there'll be a homework 6 about virtual memory for you to get some experience with that. But trust me, it'll help you a lot on the final exam. So it's good to have the practice. Okay, so there's an iClicker question about Project 4-1 and no iClicker? Okay, so can we get a sense? Okay, so let's go with thumbs up, thumbs sideways, and thumbs down. So thumbs up means you're on your way to finishing Project 4 and you don't foresee any problems. Thumbs sideways means you've started reading it and you have an okay idea of what's going on, and thumbs down means you haven't started yet. So what do we think? Haven't started? Yeah, that sounds right. Okay. All right. Okay. Cool. So let's take a quick 1-minute technology break, and then we'll keep going. Yeah. When is what? ECS. Oh, EC2. Yeah. So it's Amazon's. It's essentially Amazon's way of letting you interact with machines in their data centers. So the project will tell you all about how to use them. Yeah. You can give it to me. All right, guys. So let's reconvene. All right. So next up, we're gonna talk about the next section of this lecture. We're gonna cover disks. So really, the idea with covering disks in this class is that we want to give you a motivation for why virtual memory is designed the way it is, and the real reason is that disks are really slow. Okay. So to go over our 6th grade ideas again, or not to go over, but to focus on one of them, we had number 3, the principle of locality, and our memory hierarchy. So we've had this memory hierarchy all along, right? At the very top and very beginning of the class, we introduced CPUs, right? CPUs have kind of the fastest chunk of memory possible inside, right? They have registers. They're extremely quick, right? You can access them at sub-cycle speeds, right? But they're also extremely expensive, and they take up lots of space relative to the amount of data they can hold. Then we added in caches, right? So caches were a way to store small chunks of memory because caches are faster than memory, but they're still extremely expensive and rather small. And at the same time, we had memory backing those caches, right? So memory is kind of the main data storage unit that we interact with in the CPU, right? Our load words and store words are really meant to go to main memory. So main memory is fairly large these days. Most systems that you buy new will have anywhere from 8 gigs to 16 or 32, and so you can tell it's kind of affordable to have a lot of memory. We'll skip flash for now, and we'll introduce it towards the end of talking about disks. But what we're going to focus on today are, in fact, disks. So the thing with disks is that the cost per bit is very, very cheap, but at the same time, they're slow because they contain mechanical parts. Okay, so the idea of a magnetic disk or a magnetic medium of storing data has been around for a long time. So it's just a kind of computer memory, and the way we store data with magnetic disks, as you might suspect, is by magnetizing the surface of a certain type of material. And so this is very similar to what tape recorders do, except that this is digital storage rather than analog data storage. So magnetic disks are a type of non-volatile storage. So unlike memory, unlike caches, unlike registers, all of which lose their data when the power goes out, hard disks don't do that. So hard disks are non-volatile storage. And there are 2 types of magnetic disks that you might have seen. Maybe you haven't seen the first one. So there are floppy disks. They're much slower than hard disks. They're less dense, but they're removable. And they can take a lot more abuse than a hard drive because they're not really a sealed environment. But that lack of a sealed, kind of clean environment is the reason they're so slow and not as dense. Then we have hard disks, which are much faster, more dense. They're non-removable in the sense that you wouldn't take a hard disk and put it in your pocket and walk around, most likely. But floppy disks, you could do that, apparently. Okay, so So the purpose in computer systems of having a hard drive is to have this long-term storage. So because they can store data across power outages and other kinds of failures, they're a great thing to have in our system, right? We want to really store all of our files there so that they're not gone when something bad happens to our machine, right? If the machine crashes and restarts, the power goes out, right? And we lose everything in RAM. And so essentially the hard drive is acting as a backup for main memory. So our load words and store words are still interacting with main memory, and we can think of the disk through our virtual memory mechanism as essentially a backup for all of the pages of memory that we have. Okay. So here's a picture of the internals of a disk. So there are actually some disks floating around, and you guys can open them up. They should be open. You can look inside at the pieces. Please be a little careful. There are sharp edges inside. But you can see a lot of these parts, and I'll try to disassemble another one on video once we go through this slide. So there are a couple of components that we're interested in. So first we have an actuator. So this actuator is just a motor, right? So it's this thing over here, and this is one of the physical components in the disk. It literally moves that pointy thing across the head of the disk. And that pointy thing is called the arm. So the arm is just there to suspend this next component, which is the head. And so the head sits on a thin air cushion above the actual platter in the disk. And the head is the one that actually magnetizes and demagnetizes the disk as it's spinning under the head. All right, and then it consists of a bunch of platters. So these platters, the number of platters can range greatly. In these disks that you have are slightly larger number of platters than we have here. So I'm going to see if we can use the webcam here to try to show some of this geometry. But let's do the slide first. So when we're dealing with these disks, there are a couple of kind of geometric issues that we want to worry about, since we're interested in ultimately figuring out what the performance of a disk is gonna look like. So let's try this. Let's hope PowerPoint is okay with this. All right. So we have a disk here that's disassembled. So this is I don't know if you guys can, let's try this. All right, so can you guys see this? All right, so here's a disk that's taken apart. So this is a laptop drive from an old MacBook. And so what we have here is the lid of the drive. So this used to be a 1 terabyte drive. And you can see this arm mechanism that's moving around here, and you can see the connection to the actuator mechanism too. And so I don't know if the camera can focus this well, but on the very tip you can see those heads that are all mashed up. They're really delicate, and they kind of got destroyed in the process of taking this thing apart. Okay, so next up, inside this disk, if we take off this layer, and there should be a screw there, but that's obviously disassembled, we have these things called platters, right? So these are what are actually storing data. Since this is a laptop drive, there are only 2 platters in here. And so these platters, they have kind of a geometric breakdown that we'll use. So if you look at if you follow these imaginary concentric circles that wrap around the platter, those are called tracks, right? And then if we look at slices of the platter coming out, those are called sectors. And a series of tracks wrapping around a disk are called cylinders. So if we go back here and actually look at the diagram, right? The diagram says the same stuff. So if we look at the platter, right? So we have the platter here. We have a bunch of platters, and that head mechanism that we looked at in the beginning, all of those heads, they interleave between the different platters on the disk. And that's how the actual reading and writing happens. So the head floats on top of the platter. It doesn't touch the platter. If it touches the platter, we get something called a head crash. So this is why if you drop a computer that contains a hard drive and it doesn't have a special mechanism to try to park the heads or pull them out of the way, then they'll hit the hard drive and you'll lose your data. Okay, so when we're actually doing a write on a disk, we're going to take the bits that are streaming in and we're going to write them into tracks. So this disk is spinning, or the platters are spinning under the heads. And so the head is kind of depositing bits, you can think of, by magnetizing the disk as the disk spins under it. So we record into tracks, and those tracks are broken up into sectors, which kind of represent groups of bits. And so when we go to actually do a write, there are a couple of things that have to happen. So normally the actuator is going to park the head and the arm structure out of the way. So we have to move those onto the disk. Then we have to make sure that we move the arm so that the head actually lines up with the correct track. Once that's done, we have to wait for the disk, which is constantly spinning, unless it's trying to save power, but it's constantly spinning. We have to wait for the start of the correct sector to show up under the head of the arm. And then finally, we can start reading data at the speed that the disk is spinning. All right, and that slices a sector. Okay, so why are hard drives sealed? So if you take a look at the hard drives that are going around, you'll notice that if you take the lid off, there's this like gluish type stuff on this top metal part, and that's because the drives are actually airtight. And the reason for this is that we want the head to be as close to the surface of the disk as possible, because if you kind of think of it casting a shadow on the platter, right? We want to minimize the size of that shadow, and minimizing the size of that shadow gets us higher density in recording. So we measure this density in gigabits per square inch. So the state-of-the-art density in hard drives these days is 900 gigabits per square inch. When hard drives first came out, they were huge, and they were able to store about 2 kilobits per square inch. So following the rest of our scaling trends, right, we got this huge speed up in just 60 years. We have 450 million times as much density as we did before. So in order to enable having the head really close to the disk, we have to make sure we have a sealed environment inside. So there are 2 reasons for this. The first one is if we get dust inside, dust can get stuck between the arm and the head, and it'll end up scratching the platter. And the other reason is that a lot of the weight of the actual arm structure is supported by the air cushion that forms when this disk is spinning. So we need an airtight structure so that we get a nice predictable airflow inside. And there's some fancy math on the slide also, which I don't understand, which explains some of this stuff in terms of physics. Okay, so now we're interested in actually figuring out the performance of disks. So this will tell us a little bit more about why the rest of our computer system is designed the way it is. So we looked at the geometry of a disk, and a lot of those geometric factors are going to come into play here. So when we compute disk access time, we're worried about 4 things. So we're worried about the seek time, which is the time it takes to make sure that the head is lined up with the proper cylinder, or the proper track, right? Cylinder is just a group of tracks across multiple platters. Then we're worried about rotation time. So this is the time it takes for the disk to spin into the right place once the arm is already positioned on top of the correct track. And then lastly, we have the transfer time, which is just the amount of time it actually takes to read off the data from the disk once everything is positioned correctly. All right, so what we're going to do when we're estimating the amount of time it takes to access a piece of data is, well, the best we can do is essentially compute averages. So if we try to actually figure out where some piece of data is, where the head would be, we get this crazy formula. So we need some nice model that can kind of abstract away some of the details that aren't really relevant to getting a reasonable estimate to how long disk accesses are going to take. So what we're going to say is that in terms of rotation time, we really need to figure out the average distance of some sector to the location of the head. So on average, what you would do is you'd say the head has this probability of being in this location, and what's the probability that our data is in some other location, and then you'd integrate that across all of the possible locations. Well, we're not going to actually do that, but you end up finding out that it takes about half, on average, it takes half a rotation to get the disk and the head lined up so that you can actually read off of a track. Then the other thing we're worried about, so in detail, if we have a 7200 RPM drive, which is kind of middle ground performance these days, it's going to do 120 revolutions per second. So the platters are going to spin 120 revolutions per second. That means that we do a single revolution in 1/120th of a second, which is about 8.33 milliseconds, which means that the rotation time of a disk with 7200 RPM is going to be about 4.17 milliseconds. So it's going to take us 4.1 milliseconds for the disk to rotate halfway. Okay, so we'd plug that into the equation if we were computing this for a 7200 RPM drive. Then we're interested in figuring out what the seek time is going to be. So you can do some more math so in 186 they'll show you the math on the slides, but it doesn't actually matter. So you'll end up with this formula that you can take, on average, you'll travel the number of tracks on the disk divided by 3 to get to the right place, or to align the head up with the right track. So this means that our seek time is going to be the number of tracks we move, which is that average number of tracks over 3, times the time it takes to move across a single track, which is just a specification of the disk. Okay, so as usual, there's a catch. So our performance estimates, if you actually measure this, you're going to get probably different results in practice. And the reason is that disks have been developed for a really long time. So the disk developers, or the people that make disks, know the shortcomings of having these mechanical structures. So there's lots of magic going on behind the scenes inside the disk. So one example of these kinds of tweaks is that lots of disks have on-disk caches. So to the external world, they have no idea that there's another cache inside the disk, but there really is. And they have special algorithms that try to track what should be in that cache and what shouldn't, right? And we can have all kinds of crazy stuff going on in there because, well, the penalty for missing that cache is really high, right? We have to go invoke all the mechanical elements and get the data off the disk. So if this happens, if you request data from a disk and you end up hitting in the on-disk cache inside of the disk, well, that formula we talked about is totally bogus, and all you're going to get is the access time just for accessing that on-disk cache. But we're not going to worry too much about that because that's not, obviously we can't store everything in that on-disk cache, otherwise we would just have that on-disk cache. So that's just a little caveat to be worried about if you notice different performance when you try this out. Okay, so there's this sort of new notion of flash memory. So really it was new, 10 years ago. But 10 years ago, there was this battle between microdrives and flash memory. So microdrives are just really small hard drives. And they went head-to-head for a couple of years. So they're both non-volatile. So if they lose power, everything is fine. But there are a couple of benefits to using flash. The first of them is that flash is more durable, physically speaking. So if you take a hard drive and you throw it across the room, it is almost certainly going to break. If you take a piece of flash memory, like a flash drive, and you throw it across the room, more than likely it'll be probably okay. And the other justification for using flash is that it's much lower power. We don't have physical things that we need to move. We don't need to run motors and stuff like that. So ultimately, it came down to competition in terms of economics, right? So ultimately, we just want whatever costs the least to store our data. So disk cost is usually composed of this kind of fixed cost of motor and arm mechanics, stuff that doesn't really scale because it's not scaling at the same in the same way that most other things do in kind of the field of computer science, right? They're the kind of physical items, but the actual costs for bits to store on the magnetic media have been going down. But the problem is that we have this large kind of y-intercept value of the fixed cost of the motor and the arm mechanics. On the other hand, flash is kind of it's solid state, right? You might have heard the SSDs called solid-state disks, right? There are no moving parts, and so all the scaling happens completely in the kind of devices themselves, and we have pretty good scaling still these days. And so over time, the cost of flash kept going down, and now it's pretty competitive to have just flash instead of a hard drive at all. Okay, so if we take a look at what Apple puts in its iPods, so we start the shuffle, right? It starts with flash, a small amount of flash, then you go to the nano, still flash. If you jump to the touch, it's also flash, right? The reason they want flash in the touch is they want it to be thin, like the iPhone. And so there was this always like odd one out middle child, the iPod Classic, that actually had a hard drive in it for a long time. And, well, if you drop your iPod Classic, it's possible that you lose all your music. And, well, with streaming and stuff, nobody really stores this much music these days. So you'll notice that you can't buy an iPod Classic from Apple anymore because flash is one of the reasons for that. Okay, and actually, in fact, I don't think you can buy any mobile device from Apple these days that doesn't run completely off of flash. Okay, so how does flash memory actually work? Well, there's this NMOS transistor that has an additional conductor stuck in between the gate and the source, and this conductor is supposed to trap electrons. And the main problem here is that, well, okay, first, not a problem, but the way we figure out what's stored there is the presence or absence or of an electron or of electrons there, which represent a 1 or a 0. But the problem here is that over time, the cells degrade. So unlike a disk, where if you keep writing into the same spot, within the lifespan of a disk, that's not really going to be a problem. With SSDs, if you keep writing to the same spot, you're going to damage that cell and over time lose data. So this means that SSDs internally need to implement kind of complex tracking algorithms to figure out how to level or how to spread out writes across the internal cells inside the SSD. So lots of times when you do a write to an SSD, you'll be taking a block of data, copying the whole thing to a new place, and then doing the write while you do that, so that the writes kind of get spread out over time, as opposed to having one piece of data that goes into a location in the SSD and gets written over and over and ends up wearing that piece out. So early SSDs, because of bad firmware implementations, right, this is really complicated firmware, because of bad firmware implementations, had lots of reliability issues, but now manufacturers have been writing this firmware for a long enough time that they've kind of worked out all the bugs, and SSDs are pretty okay to use these days. And so if you're interested in more about how the OS interacts with this stuff, you should take CS162. Okay, so another iClicker question. So we don't have iClickers again, so we'll just do it by show of hands. All right, so we have this disk. It has 15,000 cylinders, so 15,000 tracks per platter. It takes 1 millisecond to cross 1,000 cylinders. And the disk spins at 15,000 RPM, which is pretty normal for a server-grade disk these days. And it takes about 4 milliseconds, as a result, takes about 4 milliseconds to do a rotation. And we're interested in copying 1 megabyte off the disk, and we have a transfer rate of 1,000 megabytes per second. And just the overhead of dealing with the disk's controller is going to be 1 millisecond. So every access is going to have that millisecond tacked on for the disk to figure out what's going on. Okay, so the formula is given to you there, and so let's take a couple minutes. So first do this on your own, and we'll see what we get with our show of hands. All right, so before you guys start talking, let's do a show of hands. So how many of you think it's A? So anyone for A? All right, how many of us think it's B? All right, C? D? And E? All right, so now take another minute, talk amongst your friends, and let's see if we can come to a consensus. Okay, so let's do another round of hands. So how many of us think it's A? A, votes for A. Okay, how about B? All right, votes for C. How about D? And lastly, E. All right, so the answer is B. All right, so let's give this a shot. So first, we're interested in figuring out what the seek time is. So the amount of time it takes to move the head onto the right track. So we know that on average, we're going to have to cross the number of cylinders that the disk has divided by 3. So in this case, we have 15,000 cylinders, and so we're going to divide that by 3, and that means we have to cross 5,000 cylinders. And we're told that it takes us 1 millisecond to cross every 1,000 cylinders. So we're going to end up with a result of 5 milliseconds for our seek time. Okay? Once that happens, once the arm is positioned into the right place with respect to the tracks, then we need the disk to rotate under the head to get into the right place. So on average, we care about half a rotation happening. So we're told that each rotation takes 4 milliseconds. So we end up with 2 milliseconds for a rotation delay. Then we have our transfer time. So this is the standard equation for transferring things over any medium, right? So we take our size, we divide by transfer rate, and that gives us the amount of time the transfer takes. So we wanted to transfer a megabyte. We divide that by 1,000 megabytes per second, and we get 1 millisecond. Okay, and then we are told the fixed controller delay was itself 1 millisecond. So if we add all that up, we end up with 9 milliseconds. Okay, so our last topic for the day, we're going to talk about networking. So if you're interested in this stuff, more about this stuff, you should take CS168. But we'll do kind of a brief overview of a bunch of networking topics. Okay, so when networks first came about, what we were really interested in was just sharing I/O devices between computers. So things like printers used to be the size of a room. You didn't just have one at your desk that you could plug in with USB. So you wanted to share these devices across different computers. Then people wanted to move programs and data between computers. So we had things like file transfer protocols developed that let us just move binary data across different mediums. Then we wanted to communicate with different people. So this resulted in the advent of email. And then lastly, what we wanted to do was take our small networks of computers and join them all up into this big network that kind of lets anyone on the network communicate with anyone else on the network. And this got us things like large-scale file sharing and the World Wide Web and all kinds of cool stuff that we rely on today. Okay, so the development of the internet. So there's this guy named Lick, who was a professor at MIT, later on became the head of ARPA, the Advanced Research Projects Agency. And he wrote this position paper sort of thing about the idea of having an intergalactic network. So lots of these universities had their own internal networks, but they were very small, right? They're kind of local to the university. There are no links that crossed large regions. And what he envisioned was that we'd have basically the internet. So we'd have this global system that connects all of the computers together, and anyone would be able to talk to anyone else that's on the network. So before that, though, we needed some things standardized. The very first of these is ASCII. So the way we store chars in C is using the ASCII standard. So we wanted a way to store characters and standardize the storage of characters across all of our computers. So ASCII became the Universal Computer Standard in 1963. Then in 1969, ARPA now became the Defense Advanced Research Projects Agency. They deployed 4 nodes at a bunch of universities. And in 1973, TCP came about, or Transmission Control Protocol, which we'll talk about in a couple of slides, that really enabled the development of the internet and enabled having reliable transmission across these long links. And ever since then, the internet has grown essentially exponentially. If you take a look at these graphs of the different nodes on the internet, they're kind of crazy. Like you can explore some of these things in 3D online, and the sheer number of hosts on the internet is really astounding. Okay, so the internet was great. It kind of let us transfer data back and forth, but we want something that's kind of more easy for humans to interact with, right? Humans all this time have been used to reading text, reading books. If you want to learn more about something, right, you would go look up a citation in a book, find the other book that's related to that thing, and go read that book. a lot of books. So what was eventually developed was this thing called the World Wide Web. So what the idea was that not only did you have these citations in your documents, but you could click on the citations and follow the citations directly to the source. And all of this information was supposed to be available for free, and so anyone could go learn about anything, right? So the history of this system was that the hypertext protocol was discussed in 1945. So there's this idea that you can jump around in different documents that cite one another. And in 1989, Sir Tim Berners-Lee proposed this system and got it up and running. And then, of course, everyone knows about 2000 when people started building all kinds of websites, some with dubious motives, and there was this burst of the bubble in 2001. And if you want to explore what the World Wide Web actually looked like in its infancy, you can check out this website called the Wayback Machine, and it has snapshots of lots of cool things over time, and the very earliest websites included. So today, of course, you can access the World Wide Web anywhere, and we're just kind of used to having all of this information at our fingertips. So a funny note on this paper written by Tim Berners-Lee about this stuff, the editor's note says vague but exciting. So exciting indeed. Okay, so getting a little lower level into the mechanics of networks. So there are really two ways we can implement networks. So we can have shared systems where we have kind of one wire connecting everything, which we saw with our bus architecture earlier when we were talking about DMA. And we can also have switched systems where we have this kind of crossbar thing. So the issue with having shared systems, like we dealt with DMA, is that we need some type of protocol to figure out who is allowed to talk on that bus at any given time. So there's this protocol that you can learn about in 122 called Carrier Sense Multiple Access Collision Detection, which figures out when people are allowed to send data over the bus, and whether or not when you make a transmission, if it's going to collide with someone else's transmission on the same network. So that's one option. So shared networks are one option. The other option is switch-based networks. So the idea here is that we have lots of point-to-point connections, but of course having these point-to-point connections actually from machine to machine is rather cost prohibitive, right? That would mean that your laptop has to be plugged into your friend's laptop, and everyone else's laptops are kind of connected together in this N-way fashion. So what we end up doing is we end up condensing these connections into these things called switches. So your machine ends up connecting to the switch, and internally the switch has something called a crossbar, which kind of connects end-to-end all of the points inside together. Now, of course, this means that your aggregate bandwidth, or the kind of bandwidth you can push through the system, is now shared across all of these devices. But that's a compromise that we have to make because it's simply infeasible to kind of connect everything together point to point from the actual location of the node. Okay, so how do networks actually work when they're all put together? So what's going to happen is we're going to have these things called links. So you can think of links in a wired network as the wires. And we're going to have our hosts on the end, so our computers presumably. And in between, we're going to have switches and routers and specialized equipment like that, whose job it is to actually direct data to the right place. And so what's going to happen here is we're going to send some data, and it's going to go to a switch, right? So when we send the data, we know only about the ultimate destination that it wants to go to, that our data wants to go to, and the switch that's directly connected to us. So it's that switch's job to make sure that once we send it data, that data actually goes through the right set of switches and ends up in the right place. And in the process of implementing networks, and we'll see this as we go through some more slides, we will introduce a bunch of concepts like layering, redundancy, lots of different protocols, and encapsulation. And these are all examples of abstraction. So we'll be using a 61C big idea here, and really a big idea of just computer science in general. Okay, and there's this fun fact in case you didn't know. Does anyone know what the logo of Cisco Systems is? Well, what is that thing? Yeah, it's a bridge. It's the Golden Gate Bridge. So fun fact. Okay, so software protocols to send and receive. So this is a sample protocol. It's kind of a dumbed down version of TCP. So you can learn about all the nitty-gritty about TCP if you take 168. And so let's say we're some piece of software, an application that wants to send data. So what we're going to do is we're going to copy that data to some OS buffer, right? This is the buffer from which the DMA engine can read from. The OS is going to calculate some checksum, right, and store it with that data so that the person we send this information to can make sure that the data is not compromised. And then the OS, when it initiates the transfer, is going to start a timer. And that timer is going to tell us whether or not we need to resend a piece of data if we don't receive any response to it. So the OS is going to send the data to a network interface, presumably by telling a DMA engine to give that data to a network interface card, and we're going to go ahead and do the sending. On the other hand, when we want to receive, what's going to happen is that the application, the OS is going to take the data that the network interface card gave us, hopefully through DMA, and copy it into an OS buffer. And then the OS is going to check the checksum that was put on the data, make sure it's okay. If it's okay, it's going to send an ACK, or an acknowledgement, back to the sender, so that the sender knows that we actually received the data that we're looking for. If the sender notices that there was no ACK received, the sender will try to resend over and over until it gets that ACK. On the other hand, if everything is okay and we have sent an ACK, then the OS is going to copy that data into the user address space, and the application is going to be able to actually continue. All right, so I have this thing. Let's see if I can get some sound here. Is this working? I don't know if you can hear this, but if you have seen Shrek, you should be able to fill in the details here. So we're going to continue on to talk about how networks have layers. Let's see if this works. Let's try this.
Onions.
They stink?
Yes. No.
Oh, they make you cry?
No.
Oh, you leave them out in the sun, they...
For your information, there's a lot more to ogres than people think.
Example?
Example? Okay, ogres are like onions.
They stink?
Yes. No.
Oh, they make you cry?
No.
Oh, you leave them out in the sun, they get all brown, start sprouting little white hairs.
No. Layers. Onions have layers. Ogres have layers. Onions have layers. You get it. We both have layers.
Oh, you both have layers. Oh. You know, not everybody like onions.
Okay, so the main point is that networks are like ogres because networks have layers. So if we want to build this network of networks, we're going to need a bunch of layers. So what does it actually take to be able to send packets across the globe? So we need to be able to put bits on some wire. Ultimately, that's the real communication medium. We want to really be able to send packets on the wire, so we need a way of converting those packets into streams of bits that the wire can actually transmit. Then we want to be able to deliver packets within a single physical network, right? So a local network of computers that are all kind of wired together. Then we want to be able to deliver packets across big sets of networks, right? So we need to connect all those networks together so that they can all communicate with one another. And then finally, once we send some data over this new network structure, we want to be sure that the destination actually received the data that we sent. And then finally, the application that we're sending data to is concerned with actually doing something with the data we sent. Okay, so what we're going to do is we're going to use abstraction to deal with the complexity of having all of these steps. So networks are like ogres and onions, and they all have layers, right? So we're going to have this hierarchy of layers. And so what's going to happen is we're going to say we have an application layer. So the application layer, all it cares about is talking to other application layers. So the application layer is going to use the features provided by the layer beneath it, in this case the transport layer, to implement some things. But really when the things at the application layer want to communicate, they're really interested in communicating with their counterparts on the other side. So if you're running a browser and you're running a messenger application inside, that messenger application doesn't really care about what wires it's going across, how reliability is achieved. All it cares about is that the message you send makes it to the other person's messaging application open in their browser. Then we have the transport layer. So the goal of the transport layer is to kind of make sure that our data makes it across the network. So there's TCP, Transmission Control Protocol, which actually gives us reliability and guarantees that our data made it across the network. And then there's this kind of filler protocol called UDP in case we don't want to pay for the overheads of having this reliable delivery. And all of this is implemented on top of IP, or Internet Protocol, which is at the network layer, and IP just provides best effort delivery. So IP says, thanks for giving me this packet. I'm going to try my best to get it across the network. If it doesn't happen, sorry, right? And so TCP is implemented on top of IP to attempt to get reliability on top of IP. And then lastly, there are two layers that deal much closer to the communications hardware. So we have the data link layer, which is worried about enforcing protocols like Ethernet, so breaking up the data into individual frames so that we can send it over the physical link. So then we have the physical link layer, which takes the data that follows this Ethernet protocol, that's encoded in that way, and then actually literally puts bits on the wire or transmits things using antennas, and so on. And there's our analogy. Okay, so we have this idea of the protocol family concept. So what's going to happen here is we're going to take a bunch of protocols and we're going to group them together and say this is what we're going to use to achieve some communication. And what's going to happen is that at each level of the protocol, right, things are only interested in talking to their equivalent on the other side. So like I said, with the Messenger app, it only cares about talking to the other Messenger app, and the way it's going to implement that is only by communicating directly with the layer beneath it. And what's going to happen as we pass data down layers, so down the stack, is that it's going to have more and more metadata tacked on. And so essentially we're putting it into more and more envelopes. And on the other side, those envelopes get unpacked as we don't need that extra data anymore. So if we want to think about why we might do this, kind of more non-computer science-y inspiration for why this might be. So let's say CEO A writes to CEO B, who's his arch nemesis. And so he writes this message, and he's going to fold up the letter and hand it to his assistant, who's actually going to take care of doing the sending. So the assistant puts the letter in the envelope with CEO B's name on it. So this is a little contrived, but the assistant doesn't really care about CEO B's address. They're just going to take it to FedEx, and FedEx office is going to put that letter, which is already in kind of a little envelope, put it into a larger envelope with FedEx's information on it, and put the name and the street address of the place where the package is supposed to go, and they're going to put that in the FedEx delivery truck. Right? So FedEx is then going to go ahead and deliver to the other company. So in this case, the CEO is taking some piece of data. He's handing it to his assistant. The assistant is then going to take that piece of data, package it up some more in another envelope, and hand it to FedEx. Now, FedEx is actually the entity that's interested in doing the transfer across. So FedEx is just interested in getting it from one location to another. And then, once we do that, FedEx gives it to the other CEO's assistant, and then the assistant unpackages the letter, takes the letter out, and hands it to the CEO. So if we look at what each level in this diagram really care about, well, the CEOs only care about the contents of the letter, right? They don't care about how it got there or anything like that. The assistants only care about the envelopes themselves, right? They put the letter in the envelope and then they hand it to someone else. And FedEx is interested in actually making sure that the package makes it from point A to point B. So FedEx is really interested in location. So if we formalize this a little bit more, we see that the CEO is interested in semantic content, so the contents of the letter. The assistant is interested in the identity of the person who the CEO is sending the data to. And FedEx is concerned with the location. So it's FedEx's job to actually get this thing from point A to point B. But everyone else, they don't care about what's going on in other layers of the system. Okay, so we already said most of this. Okay, cool. So unfortunately, FedEx is not just a point-to-point, right? You can't directly send something from a FedEx office in Berkeley to, say, a FedEx office in Los Angeles, right? It's going to go through a bunch of steps in between. So just like that, networks are not point-to-point. So there are going to be a bunch of steps that we have to take in between once it's handed to FedEx. So we have this truck, right? So the truck is going to take the FedEx envelope, give it to the sorting office, whose job it is to try to figure out where this data is or where this message is supposed to go. The sorting office is going to package it up into a crate of similar things that are supposed to go to the same place. Then FedEx is going to use its airplanes to get it to another airport. Now at this airport, they're going to send the crate to another FedEx sorting office, which is going to unpack the crate, get that envelope back out, look at where it's supposed to go in more detail, and then repackage it into a new crate that gets sent to another airport. So now the plane flies from this airport to another airport, different plane, different places. So now this airport hands it off to the final sorting office, which gives them the crate. They unpack the envelope and hand it out to the truck for delivery. So in this case, what we're interested in noticing is that our packaging keeps building up as we go to lower levels, right? And this is the same thing that's going to happen when we're actually dealing with real protocols in the network. So if we look at real protocols back in computer science land, we have this message that we want to send across to someone else. And every time we go lower in the stack, we're going to throw some extra information on that each lower level in the stack is interested in processing. So what we're going to do is we're going to put different things on the beginning and end of this message. So at the beginning, we might put things like our destination, maybe the timestamp on this message, things like that. And at the end, we're going to put a checksum that says if you do some hash function on the rest of this message or on the whole message and it doesn't match this chunk, then somebody has messed with this on the way. And then as we go down, we're going to just keep adding these headers and trailers to the beginning and end. So ultimately, we get this packet that has a bunch of headers and trailers on the end, and that's ultimately what gets sent over the actual physical medium. And then once we make it to the other side, right, so we end up back here, right, so we've sent this thing over our physical medium. We come here, and as we go back up the stack, presumably to whoever wants to receive the message, we're going to start taking off the headers and trailers that we no longer care about. So at each step, we start stripping off the information that doesn't matter, and ultimately we're just left with the message, which is really what we wanted to convey across the network. Okay, so back to actually defining our protocol. So we're going to use this thing, or we're going to be concerned with this thing called Transmission Control Protocol and IP, or Internet Protocol. And together, these form essentially the basis of the Internet. So together, they give you this wide area protocol for a wide area network, or a WAN. And so why we use TCP is that probably when we try to send things over a long distance, reliability becomes a greater problem, right? There's a larger likelihood that something along the way is going to go wrong, and so we want to make sure we ensure reliable delivery. So that's why we use TCP as opposed to UDP. And then IP, or Internet Protocol, is called the tight waist of the networking stack. So there's really one element in there, one protocol, which is IP, and everything interacts through IP. And that's how the whole network is actually able to interact with one another. So TCP, so we package up some piece of data with TCP, and then IP just makes a best effort to actually deliver that thing. Along the way, packets can be lost or corrupted. So using that protocol we defined earlier and some more enhancements to it, TCP will essentially guarantee delivery to the person we're trying to send data to. And ultimately, TCP/IP is so popular that it's used even when we're communicating locally. So even if we're communicating maybe just across one router on a Wi-Fi network, we're still going to use TCP/IP just because it's so popular and so well integrated with all of our services. Okay, so what's going to happen here is we're going to talk about how these things actually get encapsulated, or how they actually get packaged up when we're dealing with these different protocols. So first, we have some message that the application wants to send, right? We're going to take that message, and TCP is going to break this into chunks called segments, right? So it's going to take this message, break it up into pieces, and it's going to tack on a header. So this header contains information about where it's supposed to go, what its sequence number is in terms of the communication happening, what its number is in terms of segment, and so on. Then what's going to happen is we're going to tack on everything that IP needs to work. So what's going to happen is we're going to tack on another header for IP. So this is going to contain even more information about the addresses that things are supposed to go to. And then lastly, say we're sending this over Ethernet. Well, Ethernet has this parameter called the maximum transmission unit. In this case, we've defined it to be 1,500 bytes, which means we have to take all of that data we've built up so far. So as far as Ethernet is concerned, all of that stuff, including the IP header, is Ethernet's payload. So we're going to take that thing, and we have to break it up into 1,500 byte chunks, and ultimately send it as actual Ethernet frames over the network. Okay, so that's what our packets are going to look like, and ultimately these things are what really gets sent between different machines, and when we reach the other side, all of these headers are going to get stripped off once the information that are in them is used up, and our application on the other side will get the data that we really wanted to transfer. Okay, so ending a little early today. So in conclusion, over the last couple of lectures, we talked about different kinds of I/O devices. So I/O really gives computers their 5 senses. So we started out talking about the CPU. It's really the brains of the operation, but a brain can't do anything without some way of interacting with the real world. We found out that our speed ranges of our different I/O devices vary greatly. So there's not really one clean way to interact with all I/O devices. So we had these kind of nice notions of how a CPU works, and all of those abstractions were pretty clean. As soon as we start adding devices into the mix, things get really crazy. So if you look at the Linux tree, for example, for something like ARM, due to all the different platforms that ARM runs on, the device trees and the device drivers inside the Linux kernel, if you look at the source, are really insane. So it's much more difficult to understand all the different devices that Linux has to deal with on an ARM platform than just the actual Linux kernel code. Okay, so like I said, we have different ways of dealing with these devices. So we talked about polling versus interrupts. So when we're doing polling, the CPU is constantly asking the devices for data, whether or not they have data. On the other hand, with interrupts, we say that it's the device's job to tell the CPU that it either has data or wants data. Then we moved on to the distinction between programmed I/O and DMA. So the goal of DMA is to avoid wasting the CPU's time doing data transfers. So we're going to add a piece of hardware to our system that actually handles moving data back and forth between devices and memory. Then we talked about having disks for persistent storage, right? And disks are pretty slow, which justifies why we do all of that software management of page tables and stuff like that. And now disks are slowly being replaced by flash, but flash is still actually pretty slow compared to things like RAM, caches, and registers. And then lastly, we talked about how to network different computers together, and we learned how powerful abstraction is because, well, these networks are hugely complicated, but somehow they all manage to actually work. All right, thanks, guys.